guys, today we're going to start something similar to Gauss's law. We know how to calculate the electric field using either Coulomb's law or Gauss's law. And we know that Gauss's law actually helped us in calculating the electric field when we have symmetry. So that's about electric field. When we talk about magnetic field, it's exactly the same thing. We have a way to calculate the magnetic field everywhere, and that's Biot-savart law. And there is another way to calculate the magnetic field if we have high symmetry, and that's Ampere's law. So today we're going to cover those two laws, and this will enable us later on to calculate the magnetic field everywhere. So if we have a source of magnetic field, and we'll study what is the source of the magnetic field, we will be able to actually calculate the magnetic field at any point in space, regardless of the source of, or the geometry of the source of the magnetic field. So, what did we study so far in magnetism? We studied that Lorentz law that says that if you have an electric field or a magnetic field, then the force acting on a charged particle inside an electric field and a magnetic field equal to the charge times the electric field plus the charge times the velocity of that charge cross the magnetic field. And this is Lorentz law. So if we have the two fields in space, electric field and magnetic field, that Lorentz force will have a component that comes from the magnetic field and another component comes from the electric field. And if we have only a magnetic field, and that's what we're going to actually concentrate on, so the magnetic force in that case, or Lorentz force in that case, will equal to Q V cross P. And that cross product in here that ensures that the force and the velocity of that, or the direction of the motion of that particle and the magnetic field, the three of them are perpendicular to each other, and that's the right-hand rule. That's the right-hand rule that you're talking about, and or the way we have applied it in class. That's we said that those will look like fields to us. Those fingers will look like field to us. This will be the direction of the motion. This will be the direction of the force. So, and those, if you look at those three directions, direction of the field, direction of the motion, and the direction of the force, those are three vectors perpendicular to each other. So the cross product will give us a vector that's perpendicular to both the component of the motion as well as the direction of the magnetic field. We also have studied that if you have a current carries a current, a wire carries a current. A wire carries a current. Then there will be, if you put that wire inside the magnetic field, there will be a force acting on that wire. Can anyone explain that to me? Why, if we have a wire carries a current, there will be a force acting on that wire? Mahmoud? So if we have a piece of wire, and if this carries a current, so there is flowing charge of charges inside that wire, so what happens? If you put this inside the magnetic field, why will it move? Because there is a force acting on it. What is the source of that force? So why do we have a force?
We have an electric field, we have velocity, and we have magnetic field.
We have a magnetic field, we have what else?
Motion of particles.
Motion of particles. So if you have a current, that means that you have charges inside that wire that moves. And once we have a motion, then we go back to Lorentz law, and that says that if you have a charged particle that moves with the velocity v in a magnetic field, then we will have a magnetic force acting on it. And this is the same thing if you have a wire carries a current. That means simply that we have a flow of charges, more charges that moves inside that wire. So we will have a force acting on it. What will be the direction of that force? Direction. So we can apply the right-hand rule again. That's the same question that you asked me a minute ago. That we have to apply the right-hand rule again. We know the direction of the flow of the charged particle inside the wire, and we know the direction of the magnetic field. Then we can simply find out what is the direction of the magnetic force using the right-hand rule again. Then we came up with a new physical terminology that says that the magnetic dipole moment. If you have a loop carries a wire. A loop carries a wire. this loop will act like a magnet. And it will have what we call the magnetic dipole moment. And that magnetic dipole moment, it's simply I, the current in that loop, times the area. And that magnetic dipole moment is a vector quantity, and it has the same direction as the area, and that's something that we have talked about in electricity. Does the area have a direction? And that's something that we have discussed in electricity before, and the same thing applies in here. Then, if you put that loop inside the magnetic field, it will rotate. And this is simply that demonstration. So what we have in here, we have a loop that has so many turns, and I'm going to put this inside the magnetic field, that's the magnet, and I will put in that loop a current. And let's look what happens in that case. So I'm going to put a current. So I'm putting a battery, and the battery is nothing but a source of potential difference that makes the charges inside the metal to flow. So this is the loop, and it will rotate. That's simply a motor. What we have built now simply it's nothing but a motor. You have a wire that carries a current, and you put that in a form of a loop, and you put it in a magnetic field, then it will start to rotate. Why things rotate? Let's go back to physics 111. Because there is torque. That object will translate, will move from that point to that point in a straight line, will translate because there is force acting on it. But that object will rotate because there is torque acting on it. What makes object moves is forces. What makes object rotates is torque. So if we have a torque, so what makes that coil rotate is simply the torque. So the torque actually, in that case, we can calculate that torque by knowing the magnetic dipole moment, which is easy. It's a function of the current and the geometry of that wire, and the magnetic field that you put that coil in. So if we can actually somehow measure that magnetic field, we will be able to calculate how the amount of torque applied on that coil. Omar? Force on?
I don't understand what torque is.
Oh, okay. You apply a force on that door, and when you apply force on that door at some distance from the pivot, then it will rotate. And we call that thing, that quantity, what makes the door rotate is simply torque. And obviously that's not only function of the force, it's also a function of that distance. That's why that guy who made that door was very smart. He did, I think he took physics 111. He knows that he should put that knob very far away from the pivot to increase that distance, and if you increase that distance, you increase the torque. And guys, if you... Yeah, it's the same thing as the moment. And if you remember, torque, when we studied torque in physics 111 in mechanics, torque was equal to
Force to distance. Force of perpendicular distance.
force times cross distance. So that's how we ensure that they are perpendicular to each other, and the torque is a vector quantity. So we have to remember to put that arrow in there.
After if repeated and can you stop the loop from turning?
As long as there is actually wire, by what happens is at the beginning you give it a push. Just now the angle between them is between the mu and B will give you a zero torque. What angle is that? 90 degrees. So it will give us a zero torque. And if you have a zero torque, there is no rotation. Then what I do is by my hand I change that angle simply, and I let go, and it will start to rotate. What happens is it rotates. Then at some point when it has zero torque, there is no reason for it to rotate, but by inertia, which is Newton's first law, it will continue to move. Then it changes the angle and picks up torque again, and that's why it will continue. By my finger? By my finger, you mean? Oh yeah, of course, because there is torque is not that, it's not that big. Oh, you're now referring the problem to the problem in the assignment. Well, then you have to calculate how much torque is produced by this and how much torque is produced by me. And if you look at how much when you go to calculate how much torque can be produced by a human being, if you know the distance, if you assume that if you know that distance, that perpendicular distance, then you have to give an assumption or to assume how much force you can do. And usually the force we can do is our weight. This is how much force we can do. This is the assumption that you need to do in the assignment for the people who have read the assignment already. So if you assume that your weight is 100 kilogram, then you calculate how much force you can actually you can do. Then if you know that distance, you can calculate the torque. And if you compare that torque, to the magnetic torque, then you can simply see if you can actually stop it or not. Now, in that case, obviously I can stop it. It's obvious to us. Abdullah?
So we're going to need a huge current and a huge magnetic field for that thing to move a car.
You need a huge current. Yes. You need a huge current or a huge magnetic field to elevate that magnetic train, for example. Okay? And the only way to do this is, can anyone give me an idea how can we do this? How can we have a huge amount of current? Superconductor, and that's we talked about in electricity and magnetism. If you have a wire that's made of superconductor, then there is no resistance, there is no losses. The current actually you can have a huge amount of current. Okay, guys.
But we can't implement that on cars, can we? To move the wheel.
You actually no, why not? Why not? The problem is you need tracks in that case. So again, back to magnetic torque. Torque equal mu cross P, and now we can calculate actually the torque, and that's what makes that object moves, and that's actually the reason of us building motors. Then magnetic energy. Magnetic energy, that's magnetic energy equal to minus mu dot P. Mu again is the magnetic dipole moment, and P is the magnetic field. So we can simply calculate the magnetic energy, magnetic potential energy, which is minus mu dot P.
Dr. F mu was perpendicular to B. U equals 0.
The magnetic, the energy?
U equals 0.
Yes. Yes, علاء.
دكتور ازاي لما بتبقى الانجل 90 يبقى الطول دي مش نيو تايمز بي ساين 90 ساين 90
It's zero. Did I say 90? It's 0. So again, what is the direction of the magnetic field? Can anyone guess? It's either that way or that way. So what is the direction of the area now? So do you guys watch part 2 of chapter 29 at least? That was there. When we talked about torque and potential energy, that was there.
Least potential and
Yeah. Actually, it's coming. Can we wait for a minute, because I think what I do in every lecture, I review a little bit before I go into the lecture. So today we're gonna, after that simple review, we're gonna talk about fundamental law of how current can generate magnetic field. Then we'll go talk about Ampere's law when we have high symmetry. So in Biot-savart law, it's a way to calculate the magnetic field. Now, so far in chapter 29, or when we introduced magnetism, we assume that we have a magnetic field. And we did not talk about the source of the magnetic field. Now we're saying that if you have a wire carries a current, then around that wire there will be a magnetic field. And we all notice that when you walk in the street and when you go over a high power cable which has a current, then you hear noise in your radio, and simply this is because the interference between the magnetic field produced by that by that wire and your antenna, and that produces noise. Now we're very interested in calculating that magnetic field from that wires. So what we're going to do before we do this, we need to calculate how much energy can be stored in a magnetic field. So we say that if we have a coil carries a current, then that coil will have a magnetic dipole moment. It will act like a magnet, the magnetic dipole moment, and the magnetic energy in that case is minus mu dot P. So what I have here is 3 coils. This is the first coil, this is the coil. So the current goes out from here and into here, my right. Are you sure? Yes. Cross means actually the current is into the page, and that dot means that the current is out of the page. So what happens is that you have that loop and the current goes that way. Current goes out from the top and goes in at the bottom. So this is one loop. So this is the loop that carries the current. What will be the direction of the magnetic field? Sorry. What will be the direction of the magnetic dipole moment? So back again, that's what you have asked at the beginning. We should use the right-hand rule. So if this is the direction of the current in the loop, this will be the direction of the magnetic dipole moment. Again, that's the right-hand rule. So now I'm going to apply the right-hand rule in this. So the current goes out from the top and down and into the page at the bottom. So this is the direction of the current. This will be the direction of the magnetic dipole moment. So now we know the direction of the magnetic dipole moment, and the yellow lines represent to us the direction of the magnetic field. Can you guys calculate the potential energy, the magnetic potential energy? And I need the magnetic potential energy magnitude and direction. Magnitude and direction. Yeah, thank you so much. Hussein is saying, well, its energy is a scalar quantity. It does not have a direction. So guys, can you calculate the magnetic energy in that case? Mu dot P in that case number 1. Minus mu dot P. What is the angle between mu and P? 0. So dot product. What's dot product? Mu, the magnitude of mu times the magnitude of the magnetic field times cosine the angle between them. So and the cosine 0 is going back to physics 111, because that's what makes you remember sine and cosine. Work. What's work? It's F dot displacement, force dot the displacement, and that's equal to force, the magnitude of the force, times the magnitude of the displacement, times cosine the angle between the two of them. And can you give me an example of cross product that we have, something that we have studied in physics 111? Oh, torque or moment. Torque, force, cross displacement, and that's going to be, so the distance, that's F times D, magnitude of the force, times the magnitude of the force, times sine the angle between them. This is F, we have the force, and the D are in one dimension. So back to here, mu dot P, Mahmoud, mu dot P, dot product is, that's cosine. So it's minus mu, the magnitude of mu times the magnitude of B times cosine the angle between them. What's cosine 0? 1. That's the magnetic energy. Now, torque. Can we calculate the torque? It's mu cross P. and sine 0 is 0, you get 0 torque. That's case number 1. Now I'm going to change the direction, the orientation of that loop, and this is the loop. So that's my loop, and this is the direction of the magnetic field. So now again, what is the direction of the magnetic dipole moment? You apply the right-hand rule again. The right-hand rule says that current goes out from that point into this point. This is the direction of the current. This will be the direction of the magnetic dipole moment. So now look at the angle between the magnetic dipole moment and the magnetic field at 90 degrees. So now what is cosine 90? That's why you get 0 energy. What is sine 90? That's 1. So get mu times b. And same thing goes again in here. If you, this is the direction of the current. It goes out from here into this. This will be the direction of the magnetic dipole moment, and that the magnetic dipole moment now makes an angle of 0 with the magnetic field. Omar,
180.
right? Am I right? No, I'm not always right. Karim said no. The angle now between the magnetic field and the magnetic dipole moment is 180. So if the angle now is 180, you still get 0 torque. But what will be the cosine of 180? It's -1. That's why you see that negative sign on the law of the magnetic dipole. The magnetic energy has been cancelled, so you get positive work in here. Let me finish. Look at those 3 situations. Which one have the minimum potential energy? Yeah, it's the first one. This is the one that has the minimum potential energy in that case. Not the 0, and that's a common mistake that we all do. We assume that 0 is the minimum potential energy. That's not true. This is the minimum potential energy in that case. Abdullah?
What the slide is saying, but I don't get the difference between the torque and the magnetic energy.
Torque is a vector quantity that makes that thing rotate. And magnetic energy, that's the energy you stored inside the magnetic field. It's similar to the energy if you have a capacitor. If you have a capacitor, what happens in there? If you charge that capacitor, I'm going to take you back a little bit to electricity. You store energy inside that capacitor. Later on today, or maybe on Thursday, we're going to introduce something new that's coil, and that's something that stores the magnetic energy inside it, and this is the amount of the magnetic energy that we store inside. Those 2 different physical quantity. One of them that's a vector quantity, that's torque, that has a direction that makes that thing rotate. But the energy, once that rotates, that means that there is a kinetic energy. Where did that kinetic energy come from? It must come from some other source of energy, and that's the other source of energy, that's the stored potential energy in the magnetic field, and that stored the potential energy, that's mu dot p, negative mu dot p. So guys, if you have understood that part, then I would like you to actually form a group of 3 or 4, and I want you to discuss that problem together. Form a group of 3 or 4 and look at this and discuss together. Do not tell me the answer. Do not tell me the answer. We're going to vote in him. Do not tell me the answer. Keep that in mind. You can ask me anything you want if you need clarification. Can you join the group? 4, 3. Sharif, can you join Ala group? Rami, you're with that group. And more important than getting the answer is that you should talk to each other. You should share ideas.
What's the difference between the A and B?
Oh, that's actually 3 answers. A, this will rotate like this. B, this will rotate like this. C, it will not rotate at all. So took a minute to read the problem carefully, then start discussing that. Oh, Allah is asking me, how can we get the direction of the torque? Can anyone answer that? That's the direction of the magnetic dipole moment. Oh, thank you. By the smiley face. Do you remember the smiley face? Do you remember the smiley face? It's the cross product. It's the cross product. On that part of the board, we have drawn the smiley face, and we said that if we have I, J, K, then I cross J give you K, J cross K give you I, and K cross I gets you J. And if you reverse the order, you get a negative sign, and I cross I, that's 0. And I call that smiley face. So again, the difference between answer A and answer B, this is the coil. This is the coil. If it rotates that direction, that's A. If it rotates that direction, then that's B. If it does not rotate at all, that's C. Sharif, this is more important than writing the answer. You listen to them and discuss that with them is more important than. Are you done? Good. So Lena, do you have an answer? Not yet? Omar, do you have an answer? Not yet?
Okay, we know it will rotate us in sine 90 1. Okay, but how do we know that which direction?
You find the direction of the torque, and then you find the direction of the motion.
No, the direction of the torque we get?
Did you get the direction of the torque? J. Okay, guys? Guys, which one is the correct answer? Who's in for A? Just raise your hand. Group. One of each group. Raise your hand. A. No one? No one? B. Only one group? Two groups? Three? C. It will not rotate at all. So that means that we have at least three groups that they did not get the answer yet. Let's do it together. So, what should we do?
Apply the right hand rule
Apply to do what?
to get the mu cross
The magnetic dipole moment. So actually, Amr said we know that the torque it's mu cross P. Simply we need the direction of mu. Since you're asking us mainly about the direction of the rotation, you need the direction of the torque. That's what I need. And I don't really care about the magnitude of the torque in that problem now. So we need the direction of the torque. Simply we need in order to get the direction of the torque, you need to know the direction of the magnetic dipole moment and the direction of the magnetic field, and to perform that cross product. That's it. So let's talk about the direction of the magnetic dipole moment. This is the direction of the current, right? This will be the direction of the magnetic dipole moment. And if we talk about the direction of the magnetic dipole moment, in what direction will be that? Positive K. So the magnetic dipole moment is in the K direction. How about the magnetic field? In what direction is the magnetic field? It's I. Now look at the smiley face. It's K cross I. That means that the torque has to be in the J direction, positive J direction. This is the direction of the torque. This is the direction of the torque. This is the direction of the rotation. Back again to physics 111. Yeah, the door, you're right. You said, look, no. Look again at the problem of the door. What is the direction of the rotation?
Anti-clock.
It's that direction, right? That direction. This is the direction of the torque. Now, what direction is the rotation? That's the direction of the torque. Yes, it's again. Actually, we have studied that in physics 111 in mechanics. This is the direction of the torque. It's again you apply the right hand rule. So simply, if we know this, then what will be the answer? B. Okay, now, sure. What was that? That's the magnetic dipole moment. Oh, you came in late. Yeah, okay. This is one drawback of coming late. So what did we do? We needed to calculate the magnetic dipole moment. Simply you bend your hand in the direction of the current, your thumb will point in the direction of the magnetic dipole moment. So again, this is the current, right? This is the direction of the magnetic dipole moment. So again, it's the right hand rule. So now we know the answer of part A. Guys, part B. What is the potential energy mu of the loop in its initial position?
Neither.
Minimum, maximum, neither. Because we know that I have been hearing zero. It has a zero potential energy, and we have agreed a minute ago that zero potential energy is not the minimum potential energy. And let me take you a little bit back to physics 111 again, because actually all physics is related. Potential energy, gravitational potential energy. Now, what is the potential energy of that object? And what's H?
Depends on my reference frame.
Oh, so it depends on where do I choose my zero potential energy. So Sharif said that actually the zero potential energy is going to be the floor, and this will be will have a positive potential energy. It's MGH, and someone else said no. This is going to be, the table is going to be the 0 by 0 potential energy, and that's going to be 0 potential energy. Someone else will say, no, the ceiling is my 0 potential energy, and that will be a negative potential energy. So you have to specify what is your 0, but obviously your 0 is not the minimum, simply because we have agreed also that all objects would love to minimize their energy. They always go to the lowest potential energy. All objects. That's why when you leave this, it falls, so it's 0 potential energy. And if you give it another minimum potential energy, then when you give it another minimum potential energy, which is the floor in that case, it falls to the floor. It falls to the the minimum potential energy, not the 0. Yes.
I did part A in a different way.
Okay.
When I left mu خالص, I took it part by part. يعني قلت at B, current is up, magnetic field is to the right, therefore the force كده, and at A, force هيبقى كده. The two forces will make it.
That's correct too. Yeah, that's correct too. Okay, guys. So that's the answer, and that's the explanation. You can look at it and compare it to what we have said in class later on. And that's the answer. It's neither, as you said, and that's the explanation again. 0 is not your minimum potential energy. Now, let me remind you, by the beginning of that semester, when we talked about electric field, we said that we have two ways to calculate the electric field. One of them, that's Coulomb's law. So if you have Coulomb's law, it's K, the electric field from that point charge is K times that charge divided by the distance between the charge and the point that you're trying to calculate the magnetic field at. So the electric field at, and this is a vector quantity, then you have to specify the direction of that. And another way to calculate the electric field is to use Gauss's law, and we can use only Gauss's law if we have high symmetry, and we have talked about what do we mean by high symmetry. We're going to carry that same concept in magnetism, and we'll say we'll have two ways to calculate the magnetic field. One of them that actually needs a little bit of mathematics. That's a Biot-savart law that says that the magnetic field from any element that has a length dl, that has a length L, and carries a current I, will produce around a magnetic field. And if we need to calculate that magnetic field at any distance r, then simply the magnetic field will equal to a constant, which is mu0 times mu0 over 4 pi, that's just a constant, times the magnitude of that electric field, so that current, times the length cross the direction of the current divided by r squared. And that looks similar to Gauss's law, except that cross product, and we simply know how to do that cross product. This can get really, really ugly when we have a very weird shape of element carries a current. The integration gets really ugly, but if we have high symmetry, that can be simplified by Ampere's law. And Ampere's law that says again the integration over a closed loop for B, for the magnetic field dot dl, will always equal to mu0. Mu0, that's a constant, the permeability of the medium times the current. And Ampere's law, go back, mainly says that if you have an element carries a current, and if you draw around that element something that we call it Ampere's surface, Ampere's loop, similar to Gauss's surface, Ampere's loop, then the magnetic field all over that loop will be the same. And if you integrate the magnetic field dot dl over that loop, it will always equal to some constant times the current inside that loop. It will always equal to some constant, which is mu0 times the current inside that loop, and we'll get to that later today. But what's more important is how to calculate the magnetic field using Biot-savart law, which is similar to Coulomb's law in a way. Abdullah?
And Biot-savart law that r cos theta over r squared, we integrate that with respect to dl.
Yes, and I will show you an example for that in a minute. Yeah, it's simply if you need to find, if you have a weird shaped wire, then you have to, guys, this is very important. If you have a weird shaped wire, carries a current I, then all what you have to do is to divide that wire into small pieces. Each one will have a length of dl, then integrate that dl across r, you will get. Yeah, we'll see. Actually, you can do the cross product, then do the integration. So this is a weird shaped wire that carries a current I, and we need to find the magnetic field at that point. So simply, I'm going to say that I'm going to choose a small area, a small length in here that has a length of dl from of the wire, and that length, if I integrate it, if I integrate mu 0 I over 4 pi for dl across r over r squared from the beginning of the wire to the end of the wire, I will be able to find the magnetic field. Excuse me, the magnetic field at that point P. But the dB is only the magnetic field from that small part of the wire, which has a length of dl. That's dB. Let me finish this. Okay, so now remains the integration from the beginning to the end to get the total electric field, the magnetic field from all the wires. Got it? Yeah, thank you. Tariq said, well, actually now you have here r squared, and in the same equation that you put an equal sign between them, you have r cubed. So, yeah, what I did is, this is the unit vector r that has a magnitude of 1, but it tells you the direction. So if you multiply that r by r vector, you get r vector. If you multiply r hat by r vector, you get r vector. And of course, you have to do the same down here. So you have to multiply that by vector r, you get r cubed. So that equation is the same as that equation. Okay? Okay. What is the direction of the magnetic field at that point? At that point in space. So simply we go back to the right hand rule. The thumb in that way will actually will point in the direction of the current, and your hand will bend in the direction of the magnetic field. So at that point, this will be the direction of, this is the direction of the current, it's going up. This will be the direction of the magnetic field. Is it true? Because the magnetic field at that point is actually the sum of all the magnetic field of those small components from all over the wire. But if you do the same here, the magnetic field here, it's into the page. If this is the direction of the current, the magnetic field at that point is going to be into the page. From the top, the direction of the magnetic field at that point will be also into the page. So no matter what happens at that point, the direction of the magnetic field is always for that wire into the page. How about that point in here in space? It's going to be out of the page. So this is the direction of the current. This will be the direction of the magnetic field, and we can conclude from that simply, if you have a wire, the magnetic field will circulate around that wire. So if you have a wire carries a current, which is the case of that wire now, there is a magnetic field around that wire, and the direction of that magnetic field, if we assume this is the direction of the current, this is the direction of the magnetic field, circles in that direction. It circles around that direction. It circulates around the wire. So this is the direction of the magnetic field. And we use the right-hand rule to find the direction of that magnetic field. Saying that, and looking at that problem in here, I have a wire, carries a current I, and I need to find out the direction of the magnetic field at point A, B, a current carrying a wire with no remarkable symmetry. There is no symmetry of that wire, and the wire is oriented in the XY plane. The points A, B, C are in the same plane. Now, in what direction is the magnetic field contribution from the segment DL at the point A? So, positive Z. Amr is saying it's positive Z. Point A. Do you all agree? Rami? Sharif? It's only one right hand rule. You apply it smartly. That's all what you do. If the current goes straight, then the magnetic field will bend. If the current loops, then the magnetic field will be straight. Okay? Should I say that again? Should I say it again? Now, let's assume that this is the current. It's a straight wire. Then what will be the direction of the magnetic field? It will loop around it. Now let's assume that this is the current. It's a ring. Current actually goes in the ring. So, and it goes in that direction. What will be the direction of the magnetic field?
Is that the direction of mu?
Oh, it's the same direction of the mu in that case. So the magnetic field in that case, inside that wire, inside that loop, it's going to be down. It will look down. So you apply it's the same right-hand rule, and you apply it smartly. That's all. So now, from that segment DL, what will be the direction of the magnetic field at point A? So this will be the direction of the current at point A. It's going to be out of the page, and out of the page we have specified that to positive Z. How about in what direction is the magnetic field contribution from the segment DL at point B? B. It's also out of the page. It's positive Z. How about point C? Into the page. So again, Sharif, it's the same right-hand rule. Z, Z, and negative Z. Lina? How can we actually find the direction of the magnetic field from a wire? This is the direction of the current. So at that point in space, what is the direction of the magnetic field? At that point, above the wire. Right? It's into your direction, positive Z, about that point. It's into my direction, which is negative Z. Yeah, but it's out of the page, positive Z.
It is, but مش perpendicular على البوينت تاني، مش perpendicular على ايش ده قصده، مش كده component تاني.
No, this is the direction. This is you apply the right hand rule.
Okay.
Okay, and that's a very good question here, guys. This is the wire. That's the wire. At that point, what is the direction of the magnetic field? Oh, here. South, perpendicular to that plane that has the wire.
So what about right in front of the point?
Where? Here?
Like there.
There?
يعني along the point. Yes.
Oh. Right? Somewhere in here? Actually, we assume that this is a very long wire to ignore for now the end effects.
Okay.
So we assume that it's a very, very long wire. So and this is totally beyond the scope of the course. That has a little bit heavy integration to do it. That's why so far we have assumed very long wire. Okay, and that's the answer. Okay, now this. In the 3 points A, B, and C, we have concluded that the direction of the magnetic field at point A and point B are out of the page at A and B, and it's into the page at point C. Would that change if we integrate the magnetic field components all over that wire, from the beginning of the wire to the end of the wire? The answer is no. You still get the direction of the magnetic field is at point A and B is out of the page, and point C is going to be into the page. Excuse me? Yeah. Yes. Now, let's calculate the magnetic field from a straight infinite wire. So we have a wire that's infinite, and we need to find the magnetic field from that wire. So what to do? So simply, I'm going to divide that wire into small components. That's the pinkish component, small part of the wire, that has a length of dx, and that's at a distance small r from the point that we're trying to calculate the magnetic field at. I'm trying to find the magnetic field at point P, and that point P is at a distance r, from perpendicular distance r from the wire. And the wire has a current I, and the current is in the positive x direction. So what should we do? We should apply Biot-savart law, which is dB, the magnetic field from that segment at that point, equal to mu 0 over 4 pi, that's constant, times the magnitude of the current I, times dl, which is in that case the length of that segment, the dx, cross r, that's vector r, divided by r cubed. Okay? Now if I do the integration all over that wire from negative infinity to positive infinity, I will be able to find what will be the direction, what will be the total magnetic field from that wire at point P.
Has high density wire.
Yeah, and we're going to apply the same rule again when we go study Ampere's law, and we'll see the difference between the two methods. So, what is the direction of the magnetic field at point P? At point P, what is the direction of the magnetic field? It's out of the board. So this is the direction of the point P, and it's in the positive z direction. It's in the positive z direction. We get that simply. Now let's get the magnetic field. The magnetic field is going to be the integration all over those dBs, the magnetic field from that segment, plus the magnetic field from that segment, plus the magnetic field from that segment. If you divide those into small segments, Mahmoud, then we will be able to find the magnetic field if you integrate from negative infinity to positive infinity all over that equation. Now, what's dx cross r? What's dx cross r? It's dx, the magnitude of that length, times the magnitude of the vector r, times find the angle between them. So it's dx r sine theta. So this now is the angle, theta is the angle between dx and r. Yeah, well, yeah. So now what to do? Does r depend on theta? Does r depend on theta? Yes. So r does depend on theta. So actually we have to either convert that sine theta in terms of r, or r in terms of theta. Can you guys solve that integration? Can you guys solve that integration? Can you do it? Can you show me? Can you just form a group of two, only two, and try to solve? Go from that step to that step. It's a very simple integration. Omar, and that needs a solution. So you need to use a pen or a pencil. Group of two. So Lina and
No, it's all opposite of
and Shadi, Bishoy and Mamdouh, Omar, guys, you can be, the three of you can be together. Mahmoud and Tariq, Rami. Guys, group of two. R is, no, it's not constant. R capital is constant, yes. R small is not constant. It needs a little bit of geometry as well. Excuse me, that's R and that's R. Yes, you can cancel that R with that R, and here you get R squared in here. But you still have to, know, Rami, you have to know that R is a function of theta. It's obvious. If that element is somewhere in here, theta is different, R is different. So R depends on theta, and you have to keep that in mind. So you have to actually play a little bit with the geometry in order to be able to do that integration. I forgot to mention something. That distance, it's x. That distance is x. So now you have x, r, and theta in that triangle, and you have to play a little bit with the geometry.
هنسيت اوفر صح صح بس ده صح ده لا بس خلاص كان ثيتا تساوي صار ثيتا ياخد اكس اوفر مش حاجة برضه مش هنشيل الار يبقى عادي كسر ثيتا
Okay. I'd rather having it as a function of d theta. Think about that along that line. Yeah, I would actually prefer if having this as a function of, or along the line of having this as a function of d theta instead of dx. Yeah. From zero, yes. If that element dx is at negative infinity, then you can see that theta is 0. The angle between r and x is 0, and that angle here is going to be 180. Yeah. R will cancel with the cube, so it's going to be r squared. But the trick is here is to convert the dx into d theta. Yeah. Actually, it's better if you do this dx and convert it into d theta.
Theta?
Yeah. Somehow play on having that dx in the form of d theta. Yeah, but you still have theta x, and those are a function of each other. I would rather having this dx as a function of d theta somehow. Yeah, think about it.
جبنا ريشيو دي جبنا ريشيو
True. Good.
جميل
Yes.
اوكي شلت الار ساين ثيتا حطيت الار الكبير
اوكي.
دي ما فيهاش كسور تحت بقى الار كيوب دي مش هنعرف نحط ولا حاجه يعني بقى الار سكوير اللي انا جايبها
X squared plus r squared.
ضربها كيوب
Yeah, x squared plus r squared. That is your r.
دي الار سكوير
Yeah, to the power of 3/2.
باور 3 سكوير روت بعد كده باور 3.
Oh, and then you can do that integration. It's going to be an ugly integration if you do it over dx. But I would rather if you do it over, if you convert that dx in here
into dr
into d theta. Think about it.
or sin theta.
Yeah, somehow you have to convert that dx into d theta.
x equals r sin theta.
X equal r sin theta.
differentiate بقى both sides.
ممدوح.
بس يا دكتور اكس وثيتا ازاي ديبندنت على
مش عارف ازاي انا جاي.
Excuse me.
حضرتك قلت لي ان اكس وثيتا فانكشنال ايتش ار.
Yeah, look at change that x, extend that line to the end of the board. Okay, what will be theta? Will theta change?
ايوه بس لو غيرنا ثيتا
It's the same thing. If you change theta, x has to change.
عايز الجامعة دي الار اللي هو اللاين ده.
Oh yes,
فالار ده كل ما نغيره فيه ده كمان هتبقى
and x will change. R, x, and theta are dependent on each other. They depend on each other.
لما تيجي هتزيد ار هتزيد ثيتا ار.
Yeah. So you have somehow to think of actually converting that dx in somehow to d theta. Yeah, it's simple math. Yeah. ممدوح. طارق. How is it?
We started but this was wrong. We started from the beginning.
Did you do it?
اتزنقنا شفت وصلنا لحد هنا. بعد كده ما نعرفش نعمل ايه بقى.
دي اكس.
Yeah.
دي اكس اصل دي اكس هل هتبقى ار اوفر ساين ثيتا؟
What's x over capital R? X over capital R.
كوسان
Then x equal R cotan theta. What's dx in that case?
نعمل differentiation يعني.
Then you got dx as a function of theta, and you have sin squared theta in here. Then you can play with it. You get the answer.
حلو. دلوقتي كل الكلام ده كله حلو. بعد كده دي اكس ار ساين ثيتا على ار كيوب. ساين ثيتا دي شلناها وحطينا بدلها اللي هي اوبوزيت على الهايبوتنس. في ار راح مع الار بقى واحد على ار كيوب. دلوقتي انا عايز اشيل الار ده احطه ان ترمز اوف اكس.
Yes, actually, I would prefer that you do this. Yes, no. I would prefer that you convert that R and dx into something as theta. I would rather leave theta. I would rather leave sin theta and somehow convert this into integration over the angle theta. No, it's going to be much simpler. Trust me. Then you got, what did you get?
يعني عجبت الار هنا ومش عارف اتصرف واحد على يعني عايز دي اكس تبقى ان ترمز اوف ار.
Let's go back in here.
انا جبت ساين ثيتا جبتها من الار الاوبوزيت على
I would leave the sin theta.
يعني نسيب ساين ثيتا.
Yeah.
طيب وعايز يجيب الار بقى ان ترمز اوف
Yeah. Did you do it, guys? Are you done? You got the answer?
لسه احنا وقفنا على ماينس ساين سكوير ثيتا كوسك سكوير ثيتا.
علاء. Okay.
كوسك دي على دي تروح صح؟ دي هتروح.
Perfect. Good. Yes.
تطلع الاول بقى مش نفس الارقام.
You still have to get rid of that R.
يعني ار
That R.
يعني ار كابيتال
No. Yeah.
تيجي بالسهم بقى.
You have to get rid of that R. Are you done? So So are you done? You do it?
Yes. بس طلع ماينس في الاخر كده.
Integration of a cosine is negative cosec squared.
Yes. So you got the negative sign? It's a negative cosec or is it cosec?
I think it's negative cosec.
Okay. Okay, guys. I have one group that almost got that. So let's see how to do it. Let's see how should we do it. So we said that we're gonna do that integration. We need to do that integration somehow. So I said that R simply is capital R from the geometry, capital R over sine theta. Am I right? Sine theta equal to R over capital R, and then I'm gonna replace small r by capital R divided by sine theta. So each time I see small r, I'm gonna remove it and put instead of it capital R over sine theta. If you do this, you get in here r squared sine squared theta. So we get 1 over r squared sine squared theta. But you still have that dx in there. You have to get rid of that dx somehow. You have to convert that dx into d theta. So what I did is, we said that, okay, tan theta equals to r over minus x. Why negative x? Because it's in the negative side. It's in the negative side. So that's the mistake that you have done. So you get in here x equal to minus r cotan theta. Now differentiate that equation here. So if you differentiate that equation here, you get dx equal to negative r negative 1 over sine squared theta, which is cosec squared theta, d theta. Now put all those in that equation again. Put the value of r in here, put the value of dx in here. That's what you get. That's what you get. Oops. That's what you get. Use your I. Mu 0 I over 4 pi times d theta over r sine theta. Right? Look at that integration. The integration now is from 0 to pi. Before you go, please, just this is very important. 1 minute. The angle theta, if that element is at infinity, that angle theta is 0. If that element is at positive infinity, that angle theta, it's 180. So you do the integration from 0 to 180 for sine theta d theta, and that's what you get. And if you plug in the values for theta in here, you get mu 0 I over 2 pi r. Did you see? That was not that an easy task today to use Biot-savart law to calculate the magnetic field from a straight infinite wire. On Thursday, we'll learn how to do it again using Ampere's law and compare the two methods. Thursday.